So I'll talk about liquid crystal superconductivity, etc., and then we'll see how far we go. So one of the things that I tried to emphasize in my last lecture was this aspect of phase transitions that is very important, which is the spontaneous breaking of symmetry. We have found out that in the case of the Ising model, for example, it has up-down symmetry, but the ordered state picks up either up magnetization or a down magnetization, and that way the ordered state breaks the symmetry of the original Hamiltonian. And of course, different systems will have different kinds of symmetry, and so the symmetry that is broken, will vary from one system to another. One thing that I had mentioned that again yesterday was the phase transition from a liquid to a crystal, and there the symmetry that is broken is a continuous symmetry. It's a continuous symmetry of translations. Whereas in the Ising model, the symmetry that was broken was a discrete symmetry. It was a symmetry that corresponds to the operation where all the spins are reversed. So now if we look at situations where the symmetry that is broken is the continuous symmetry, then an interesting thing happens. And the breaking of the symmetry gives rise to the occurrence of a new mode of excitation, which is known as, goes under the general name of Dumbo-Goldstone modes. And I'll try to explain what this corresponds to. So, I mean, these Dumbo-Goldstone modes typically in a broken symmetry phase corresponds to the presence of massless excitations or gapless excitations. What do I mean by that? It means that the excitations will be typically characterized by some kind of a wave number. And as the wave number goes to zero, the energy associated with this excitation also goes to zero. And whenever there is a phase with a spontaneously broken continuous symmetry, there will be such modes. And these modes, of course, will then contribute to various low temperature properties of the system. So that is another aspect of phase transitions, which is some kind of an emergent aspect, in the sense that this new excitation that is present in these systems is possible only when there is this phase transition where a continuous symmetry is spontaneously broken. So I'll just give you a couple of examples. As I just mentioned, when one goes from a liquid to a crystal, the symmetry that is broken, the symmetry under uniform translation. So uniform translation, which means that all the ions are being translated by the same amount, that doesn't change the energy because the Hamiltonian is invariant under uniform translation. But if I want to look at it, this translation from the point of view of some kind of an excitation, uniform translation basically means that the k vector associated with that translation is going to be equal to zero. Because how does the k vector come in? It comes in as a phase factor into the ik dot r. And if that is to be uniform, then this k has to be equal to zero. But you know that when k equals zero, a uniform translation, that doesn't cost any energy. So by continuity, if you look at such displacements, not exactly k equals zero, but a small value of k, the energy of that will be small, and this energy will go to zero as k goes to zero. Again, it's important to realize that k going to zero corresponds to uniform translation, which is a symmetry of the Hamiltonian, and as a result, it does not cost any energy. So by continuity, one also expects that k goes to zero, not exactly zero, but small value of k, then this will cost some energy, but that energy will be small. And for a crystal, you know what these excitations are. The crystals are, I mean, some of you have studied solid-state physics. There we talk about phonons. The phonons are associated with the vibrations of the ions that are sitting on the lattice. And there we have acoustic phonons. And acoustic phonons, their energy goes to zero as k goes to zero. So that can be thought of as some kind of a broken symmetry or a Dumbo-Goldstone mode. A situation which is perhaps less familiar is when you are looking at a ferromagnet. But the ferromagnet, of course, has a spontaneous magnetization. The average magnetization points in some particular direction, but it can point in any direction because the Hamiltonian is again invariant under a simultaneous rotation of all the spins. We are talking about not Ising model. Ising model is a discrete model, but we are talking about the Heisenberg model, where you have the spin vectors and you have an interaction which is SI dot SJ, which is, of course, invariant under a uniform rotation. So again, the same kind of argument will tell you that if I rotate the spins not uniformly, but with a k vector which is small, this is something that is illustrated here, that in the upper line, you have this spin vectors, which are being rotated as one goes from here to there and there. Can be seen more clearly if I look at the projection of this vector in a plane perpendicular to this direction. And so this projection is basically rotating, and the k vector associated with this rotation is the k vector of the excitation. Now, if k goes to 0, again, the uniform rotation, that doesn't cost you any energy. So the energy of such an excitation for a small value of k will be small, and this energy again will go to 0 as k goes to 0. So this is again another example of a Nambu-Goldstone mode, which is associated with this broken continuous symmetry. And there is a name for this excitation. When you have a ferromagnet, Heisenberg ferromagnet, then one has something called spin waves. And the spin waves are basically these excitations, where spins are rotating by a small amount about the direction in which they are pointing in the ordered state. And the k vector associated with that rotation is small, and the energy of such excitations again will be small, and it will go to 0 as k goes to 0. That's why it is called a massless mode. And the presence of this massless modes in the ordered phase, in which a continuous symmetry has been broken, is another manifestation, so to speak, of this kind of phenomena that we have been talking about, that because of these interactions and things like that, one gets to states which are interesting and which cannot be easily guessed just by looking at the Hamiltonian. And in addition to this long-range order, there are also excitations which are characteristic of this ordered phase, and these are called Nambu-Goldstone modes. And these modes basically play an important role in the low temperature properties of the system. So this is something that you should keep in mind. And then what I want to discuss the next is some kind of a simple theory, which is called a Landau theory of these phase transitions, and first order, second order phase transitions, things like that should be clearly seen in that theoretical description. So the first thing to sort of formulate a Landau theory is basically to define the order parameter. The order parameter is something we are looking at situations where the low temperature phase has some kind of an order. Ferromagnetic order in the case of magnetic systems, it has crystalline order in the case of liquid to solid transition, things like that. And this ordered state has to be characterized in terms of a suitably defined order parameter. And this order parameter has to be chosen carefully, depending on the symmetry that is broken. That sort of dictates what kind of order parameter you have to describe that symmetry broken phase, in the sense that, as we have seen, for example, in the case of a Ising model, ordered state can have non-zero, must have non-zero magnetization, but the magnetization can be positive or negative, depending on whether the spins are predominantly pointing in the up direction or in the down direction. So the order parameter then is something like a magnetization, which is a scalar in this particular case, because we're just looking at plus minus 1. But the order parameter, of course, will be non-zero in the ordered phase. It will be 0 in the high temperature paramagnetic phase. Only in the low temperature ferromagnetic phase, after the phase transition, the order parameter will acquire a non-zero value. And the order parameter has to be chosen in such a way that it distinguishes between these two ordered states. One ordered state corresponds to a positive magnetization, other ordered state corresponds to a negative magnetization. And the fact that one has a positive value and the other has a negative value tells you that these two ordered states, although they're thermodynamically in some sense equivalent, system can go into either the up state or the down state at the transition. But once it goes into the up state, then the order parameter has a positive value. Goes into the down state, the order parameter has a negative value. So the order parameter then distinguishes, that is what I'm saying, distinguishes between different equivalent symmetry-related ordered states of the system. So this also tells you that instead of an Ising model, if I have a Heisenberg model where the basic spins are vectors, there the order parameter also has to be a vector, because this basic spin leads to a ferromagnetic state in which the magnetization, again, the average value of the spin, points in some direction. But this can point in any direction. All the ordered states are in some sense, in that sense, equivalent, that it's pointing in the, let's say, Z direction, then you get one ordered state. It points in the Y direction, then again, we'll get a different ordered state. And the order parameter, again, has to distinguish between these two. And that's why the order parameter is chosen to be a vector magnetization. So depending on the kind of order that you have in the symmetry broken state, one has to choose an appropriate order parameter, which will be 0 in the high temperature phase And as the system orders, as one goes through the phase transition, this order parameter will pick up a non-zero value. And this order parameter has to be defined in a particular way that it should distinguish between different but thermodynamically equivalent symmetry-related ordered states of the system. So for the Ising system, and the order parameter is a scalar. For if I look at a Heisenberg ferromagnet, the order parameter is a vector, and depending on what kind of order is taking place, we'll see later on that one can have different kinds of order parameter. The crystalline solid, I'm not going into detail because that goes into Fourier transform and things like that, which at this point will take some time. But the basic concept should be clear from the magnetic systems. So once one has defined an order parameter, then one tries to formulate some kind of a theory. And that theory, as I said, is the Landau theory of phase transitions. It is not an exact theory, but it gives you a very good idea about what is going on at a phase transition. So here, of course, we are talking about a thermodynamic system. So one of the important things is the free energy, appropriate free energy. It could be Hensbaum's free energy. It could be the Gibbs free energy. That depends on the ensemble that you are in. Instead of going into those details, I'll say that in general, there is a free energy. And in Landau theory, this free energy is written as a power series of the order parameter. So once you have defined the order parameter, then you know what it is. I mean, it's a scalar or a vector or a tensor or something like that. And then one writes the free energy as a power series of this order parameter. Assuming that this order parameter is small, if you're near the transition temperature, the order parameter is going to be small. And then one can do a power series expansion and keeps only the lowest non-trivial terms, lowest terms that are necessary to make this free energy well-behaved function of the order parameter. And there again, the symmetry plays an important role. That in the power series, the terms that will occur will be determined by the symmetry of the order parameter. And in particular, one has to write these terms in a particular way, in such a way that the free energy remains invariant under the particular symmetry that you are interested in. So just to give you an example, the simplest example is this sort of Ising model kind of transition, where the order parameter is basically a scalar, which can take positive and negative values. So if I now want to write the free energy as an expansion in this order parameter, now we are allowing the order parameter to vary from one point in space to another. X is basically a position index, and phi in general will depend on X. But we are expanding the free energy in powers of this phi, and the symmetry that one is talking about is up-down symmetry. That positive value of the magnetization or a negative value of magnetization, they are equivalent in the sense that they should have the same free energy because they are related to each other by the symmetry operation, which is a symmetry under reversal of all the space. So that dictates that only even powers of phi will occur in this expansion. So that is what I have written down here, phi squared and phi to the fourth. And since I'm now saying that the order parameter can vary in space, there will be some kind of a cost associated with spatial variation of the order parameter. So the gradient of phi also comes into the picture, but it comes with a second power. So you see that this free energy is invariant under phi goes to minus phi, a global change of sign. All phi x going to minus phi x will not change this free energy because it has only even powers. So this just tells you about how one can generally construct some kind of a Landau theory. That once you have identified the order parameter, then you write the free energy as a power series expansion in that order parameter and keep only those terms which have the right symmetry. So for a system with up-down symmetry or phi going to minus phi symmetry, one has only the even powers. And the coefficients that occur in this expansion, there are three coefficients here, R, C, and U. They in general depend on the control parameter, which is temperature in most of the cases. But again, simplified level, one says that the C and U are independent of temperature, but this R parameter has a dependence. And this R parameter depends on temperature as some constant multiplied by T minus Tc. Tc being the temperature at which the phase transition occurs. Okay, so this is the structure of Landau theory. You have the various terms, these are phenomenological terms. And in general, it is not easy to find out a priori what these terms are going to be. But one basically takes this C and U as positive parameters. And this parameter that comes with the first term that one says is proportional to T minus Tc. So this defines this functional. Let's call it a functional because this phi x itself is a function, and so the value of this f depends on the full function, how this phi varies in space as a function of this capital X. So given this, then the prescription is that you have to find a minimum. Thermodynamic principles tell us that the equilibrium state corresponds to a minimum of appropriate free energy. So basically what then one tries to do is to find the value of phi, or the whole function phi of x, which will minimize this free energy. And simplest approximation in most cases, I mean, if you look at the ordered state, and the ordered state is homogeneous, it doesn't depend, I mean, the order parameter doesn't depend on which point in space you are looking at on the average, in the actual thermodynamic state. So then one says that phi x everywhere is going to be equal to the average value of the order parameter. So this is a simple approximation, which is called mean field theory. In general, there will be fluctuations, and the Landau theory basically ignores those fluctuations, but that is a more advanced topic, so I don't want to go into it. Simplest approximation is the phi x is the same at everywhere. In the ordered state, this phi average will be non-zero, and in the disordered state, this phi average will be 0. So if you do that, then this expression becomes very simple, because the x dependence disappears, the gradient term disappears, and so you basically have r phi average squared plus u phi average to the fourth. And this is basically a total, then the integration over this dx will give you a factor of the volume. And then you are supposed to find the minimum of this as a function of this phi average. And that's a very simple problem. So this is the whole point, that in Landau theory, one is writing the free energy as a power series in the appropriate order parameter field, and keeping terms only those terms which are allowed by symmetry. And then one is making this assumption about how these coefficients depend on the temperature. Then one is making this mean field approximation, saying that this phi is the same at every point in space. And then you get basically a function. Now it is not a functional anymore. It's a function of this phi average. And u doesn't depend on temperature. R depends on temperature in a particular way. Now this function, you can easily minimize, of course. What is more instructive is to plot this function as a function of its argument. So this is basically the function, and the temperature dependence is something that is shown here. And let's say if t is bigger than tc, this is the line that you get, t bigger than tc. T bigger than tc basically means that r is positive, and you have a function which is here. Both these coefficients are positive. So you have basically a symmetric function, which is the minimum when this argument is equal to 0. So this is the kind of shape that you get of this function. And there is only one minimum. The minimum is when the order parameter is equal to 0. As you come closer and closer to Tc, this coefficient becomes smaller and smaller. The curvature at this point, which is given by this coefficient r, gets smaller and smaller. At t equals Tc, the first term doesn't contribute. You have a fourth power, and so you have a very flat function here, which remains constant here at the origin. But still, there is only one minimum. Only one minimum, that is at phi average equal to 0. But the behavior changes when this r becomes negative. R becomes negative basically means that at this phi average equal to 0, you have a maximum, and then there are two other minima which develop. So t less than Tc basically then corresponds to the curve that is like this. I'm sorry. That is like this, that it has a maximum at phi average equal to 0, but it has two minima at some non-zero value of phi average. This is what one would expect, because in this system, you know that there are two ordered states. One corresponds to a positive magnetization, one corresponds to a negative magnetization, but they should have the same free energy. And that is basically what is going on here, that you have these two minima, which are symmetric in the sense that the free energy here and free energy there are the same. But the minimum occurs at a non-zero value of phi average, which basically means that system now can be in the ordered state. And the order parameter will have a value which corresponds to the value of phi average at one of this minimum. It could be positive or negative. As one goes to lower temperatures, this coefficient becomes even smaller, and this minimum moves there, this minimum moves there. So the value of the order parameter is going to increase as one goes to lower and lower temperatures. So this is precisely what happens in a phase transition, that order parameter is 0 when the temperature is above the critical temperature. And then it begins to, this is a continuous phase transition, because these two minima, which represent the ordered state, develop continuously from this point. So if you are very close to Tc, these two minima will occur at values of phi average, which is also very small and which goes to zero continuously as t goes to Tc. So it's a continuous phase transition, as you see in the Ising model. And this theory then tells us about how this phase transition can be described theoretically. I also mentioned that now there are these two minima, of course. These two minima, one corresponds to the positive magnetization, this corresponds to negative magnetization. But initially there was a minimum at m equals 0. So as one reduces Tc, T to temperature less than Tc, then the system goes into either one of these two, either this or that. And once one gets into one of these minima, to go to the other minimum, one has to climb then this free energy barrier. And this is what I was talking about in the last lecture, that once the system goes into a state of positive magnetization, then it cannot go to a state with negative magnetization if the system is sufficiently large. So this is what, in some sense, describes the whole phenomenology of the phase transition. So one thing that I want to point out, and last time we were also talking about first order, second order phase transitions. So here we are getting a second order continuous phase transition. But again, there are Landau theories which will give you a first order phase transition. And it's very easy to see where that comes from. So here we have only even powers of the order parameter. And that came from the symmetry that as I change the sign of the order parameter, then that's a symmetry operation, that the free energy shouldn't change. So you should get only even powers. But there are situations, and some situation I'll describe later on, where the order parameter doesn't have this symmetry, up-down symmetry, or symmetry between positive and negative values. And there, the Landau expansion can contain odd powers. So no up-down symmetry, odd powers of the order parameter appear in the Landau expansion for the free energy. And here I have written down a typical situation where you have a second power, third power, fourth power, and higher powers are neglected, again, using the same kind of argument as I was telling you earlier. But then, again, the problem is to find the minimum of this f as a function of this order parameter s. And here we are showing the plot. And this plot now looks quite different from the plot that I had in the previous transparency, where the free energy was invariant under s going to minus s. But here, of course, because of this cubic term, free energy is not invariant under s going to minus s. And in particular, this is something that you can, I don't want to spend a lot of time on it, but you can this is a simple function. So you can easily find how it depends on s. And for a positive w, what is going to happen is something that is shown like this. So at very high temperatures, you still have a minimum sitting at the order parameter equal to 0. That's the disordered phase. As you go to lower and lower temperatures, this R is again T minus Tc. So as you go to lower and lower temperatures, a new minimum develops at a finite value of S. And as you go to lower and lower temperatures, this new minimum basically becomes lower and lower. So at the transition temperature, the free energy at the minimum at is equals 0, and the free energy that you have at this new minimum, which of course corresponds to a finite value of S, which corresponds to the ordered state, these two things become equal. So this is the temperature at which the transition should occur, in the sense that as I go to still lower temperatures, then this secondary minimum that is developing, that goes to a lower temperature, a lower value, I'm sorry. So, I mean, this is for temperatures higher than the transition temperature. This is this one. Last one is for temperature equal to the critical transition temperature, where the two minimum have the same free energy. And then as I go to temperature lower than Tc, then this minimum, the free energy at this minimum, becomes still lower. So then there is a transition from this one to that one, because the system should be in a state with the lowest free energy. And that gives you a change of value of the order parameter from 0 to a finite value. So order parameter S changes discontinuously at T equals Tc, and this gives you a first order transition. And this also shows that near Tc, you have two local minima. One corresponds to the disordered state, one corresponds to the ordered state. At T equals Tc, these two minima have the same free energy, so they are degenerate. But above Tc, the minimum, the disordered minimum have the lower free energy. Below Tc, the ordered minimum have a lower free energy. So there is a transition from the disordered to the ordered state as one goes across Tc. But both of them are locally stable at temperatures near Tc. And this is what leads to this supercooling, superheating that we had mentioned at the very beginning. In a first order phase transition, it is possible to go to a temperature which is lower than the critical temperature, but still the system can be in the disordered phase as a metastable state. And that leads to this, what I just told you about is supercooling. And the other way, if you start from the ordered state and go to higher temperatures, the ordered state can be maintained till a temperature which is slightly higher than the transition temperature. That is a superheating. And that occurs because the free energy in the Landau picture has two minima, and both of these minima can persist as local minimum when the temperature is close to the transition temperature. So again, the basic phenomenology of both this kind of phase transitions, continuous as well as discontinuous, can be understood from this Landau picture. And again, the most important factor is the symmetry of the order parameter, in the sense that the order parameter has this plus minus symmetry. Then you don't have this picture. You have the picture that I had in the previous transparency, and there you have a continuous phase transition. But if it doesn't have this plus minus symmetry, which allows this cubic term, then that automatically says that there will be a first order phase transition with associated superheating, supercooling, this kind of metastability that you see in ordinary first order phase transitions, like the crystallization temperature of water. So I hope I have given you basically a very simple framework in which you can understand what is going on in these phase transitions. And again, the emphasis is on symmetry, because the symmetry determines what terms are allowed in the Landau expansion. Okay, so this is also sort of general theory. Then I go on to tell you a little bit about phase transitions in some of the systems that are of interest. So that is what is coming next. And here I'll go through this description sort of quickly, because all the basic things that are sort of required to understand phase transitions, those things I've already told you about. So as I said, the basic thing is that given a particular phase transition, one has to look at what is the appropriate order parameter, and then one looks at Landau expansion in terms of this order parameter, and the order parameter is such that odd powers are allowed, then typically we have a first order phase transition. If only even powers are allowed, then we'll have a continuous phase transition. So let's see, how does that translate into actual physical systems. So I want to spend a little bit of time on liquid crystals, because these systems exhibit a variety of different phase transitions, different phases and phase transitions. And the basic physics is this, that you have this rod-like, instead of having spherical particles, you have this rod-like particles. And of course, they're interacting with each other and so on and so forth. And as you cool the system, again, this liquid crystals typically go from, this is thermotropic liquid crystals. Temperature is the control parameter. So it goes from a disordered phase to different kinds of ordered phases. What I mean by different kind is that since these molecules have like a rod-shaped molecule, then there is an orientation associated with these rod-like molecules. There is, of course, a position associated with the center of mass of these rod-like molecules. The positions can order or not ordered. So there is a positional order or transitional order. But then one can also talk about the orientational order or disorder associated with these rod-like molecules. So this both kinds of order is possible. So high temperature phase is the isotropic phase, when there is no transitional order. So it's like a liquid. Center of mass, if I look at positions, like liquid, and no orientational order. Also in the sense that these rod-like molecules are oriented typically in all different directions. So there is no special direction that is picked up by these molecules. Then as you reduce temperature, depending on the actual system that we are talking about, most systems actually show this behavior, that the first order that takes place is the orientational order. So again, this phase is called the nematic phase. This is called the isotropic phase, in the sense that there's no orientational order, and it's a liquid as far as the center of mass is concerned. Here also you have a liquid. The positions of these centers of mass are again distributed as they would be in a liquid, but preferentially they are oriented in a particular direction. So there is orientational order, but no transitional order. And this is the characteristics of nematic phase. And the reason that these things are called liquid crystals is that this is a liquid, this is also a liquid. But these two are distinct from each other, because in this case, there is no orientational order, whereas here you have picked up non-zero value of the appropriate orientational order parameter. So if I now want to describe this phase transition, I have to find out an appropriate order parameter for this. And the long axis of the ith molecule. So here there is a well-defined long axis. So in that direction, if I draw a vector, that tells you about the orientation of this molecule. And then one can say that this is the order parameter, and this acquires a non-zero average as one goes from here to there. But that doesn't, again, you have to think a little bit about it, and this will tell you that this is not the right description, because these molecules, their heads and tails are basically identical. So if I want to associate a unit vector associated with it, then it's not clear whether I'm going from this end to that end or that end to this end. Both of them are equally good descriptions. There is physically no difference between something that points from the tail to head or something that points from the head to tail, because this can just turn around and the head becomes tail and tail becomes head. So this unit vector is not a suitable order parameter because it doesn't contain this requirement that n and minus n are equivalent, physically the same. So we have to come up with a different order parameter, and something that does not change when this n is switched to minus n. So this is different then in the sense of a ferromagnet, Heisenberg ferromagnet, in which you have an order parameter which is a vector. And that is true because the spin vectors, there is in some sense an arrow. I mean, when I draw the spin vector, I always put an arrow at one end, and that distinguishes that end from the other end. But here, there is no difference between this and that end. So your order parameter has to be invariant under n going to minus n. So then one can construct such an order parameter, which has two factors of n, because now here, as n goes to minus n, then this order parameter will remain unchanged. And this is a tensor order parameter, and one constructs it in a particular form, which is sort of consistent with the rotational invariance of the system. When you have a second rank order parameter, which is rotational invariant, then you have to have this kind of a tensor, which involves the components alpha and beta are the Cartesian components. So 3 dimensions, it's a 3 by 3 matrix, and that's a second rank tensor, and this is the appropriate order parameter. Now the interesting thing is that in the Heisenberg case, s going to minus s, m going to minus m, the order parameter, which is the magnetization, negative value of that value of that order parameter with a change sign, these two are equivalent. So Lambda expansion contains only even powers of this order parameter for the case of a Heisenberg ferromagnet. But here one can easily see that that kind of invariance is not there. So if I want to write down a Landau theory for this order parameter, it will contain cubic terms, a third power. And that automatically tells you that this transition is expected to be a first order transition. And that is precisely what one finds in experiments also, that the isotropic to nematic transition in liquid crystals is essentially first order transition. It could be weakly first order, but there is a discontinuity at the transition. So this tells you about the importance of choosing the order parameter in a physical way. And once you have chosen the order parameter, then one can find out, that defines the symmetry of the order parameter. And then you can find out, what kind of terms are going to occur in the Landau expansion. And then from there, you can sort of test what kind of phase transition the system is going to exhibit as that kind of order sets in. So here, this symmetry that this end and that end are equivalent tells you that the order parameter cannot be a vector, it has to be a tensor. And as soon as you have come to that conclusion, then when you try to construct a Landau theory, you will find out that there are odd powers in that Landau theory, which gives you a first order phase transition. I just want to mention one more liquid crystal phase transition. There are many other liquid crystal phase transitions. So I've told you about the nematic phase. It is still a liquid as far as the center of mass positions are concerned. As far as the orientations are concerned, they are preferentially oriented in a particular direction. Now, as you go to a temperature which is still lower, then this transforms into another phase, which is called a symmetric phase transition, where some positional order begins to develop. And as you can see here its positions are completely disordered, but here the positions have been ordered in such a way that they are forming these layers. And so there is transitional order in one direction, in this direction, which is perpendicular to the layers. The layers are repeated as I go in this direction. So there is periodicity in that direction. But within a layer, it is still a liquid. So this state exhibits features which are present in both liquid and solid. Solid, of course, have crystalline solid has positional order in all three directions, but here the order appears in one direction, liquid-like in the other two directions, and of course the orientational order that you had in this phase remains there. So again, this transition is something that is seen very commonly in liquid crystals. And so if I want to now describe this transition, so I have to find out what is the order parameter that describes this transition. And this order parameter again has to describe this density waves. So as I go in this direction, normal direction to the layers, basically the density changes periodically. Here the density is high, here it is low, again high, again low, etc. So there is a periodic modulation of the density in the z direction. And the amplitude of that periodic modulation is now the correct order parameter. So that is what I have written down here. The average density now, we are talking about center of mass density, is the background. And then there is a periodic modulation with a wave number q. Q is 2 pi over d, where d is the layer spacing. And the amplitude of this psi is going to be the correct order parameter. And this psi can be, psi is a number, but it can be a complex number because this modulation that you have in that direction can have a phase. And so the phase of that is contained in this order parameter psi. So order parameter is now a complex scalar order parameter. And that basically gives you a Lambda expansion, which is very different from the Lambda expansion that you get for the isotropic to nematic phase transition. It has only even powers. So the transition that one gets from going from here to there is supposed to be a continuous phase transition, and that is what one finds in experiments also. So there's one more thing that, don't worry about this. This will come up later on when you talk about superconductivity. So just these two examples that I'm talking about for liquid crystals tells you that depending on the kind of order that you are trying to describe, the order parameter, of course, will change as you go from one kind of order to another kind of order. And this order parameter will tell us, the symmetry of the order parameter will tell us then what kind of terms appear in the Lambda expansion. And that, in turn, will tell you about what kind of phase transition system is supposed to exhibit. In this case, I've just talked about two phase transitions. One is the orientational ordering phase transition, and there this order parameter has odd powers in the Landau series expansion. Whereas if I now look at the onset of this density wave in the Symmetric phase, then this order parameter is just a complex scalar, and again, one has only even terms in the Landau expansion. So the previous transition would be first order, but this one would be a continuous transition. So this basically tells you about the general framework for describing phase transitions. Again, I've been emphasizing it many times that the symmetry considerations are important because that determines what kind of order parameter you need to describe this transition. Once that is known, then you find out what kind of terms should appear in the Landau expansion. And from that, at least in a simple sense, in a mean field theory sense, you will be able to tell what kind of phase transition is going to take place in that system. So this basically ends my general description of phase transitions. The spontaneous symmetry breaking is an important phenomenon that leads to new excitations, which I just mentioned, the Goldstone modes. And trying to understand the nature of the phase transition, again, symmetry plays an important role because this symmetry gets embedded in the order parameter, which in turn tells you about what kind of Landau expansion you can have, and that in turn tells you about what kind of phase transition you're going to have. So I have talked about magnetic systems, both Ising magnet and Heisenberg magnet. I have talked about now a few liquid crystalline systems. The last system that I want to discuss a little bit, because that's a very important problem, that is superconductivity. Again, you know the phenomenology of superconductivity, which was discovered by Cavendish oneness many years ago, more than 100 years ago. So basically what one is looking at is a metallic solid, and then one is looking at its resistance as a function of temperature. And high temperatures, one has a resistance which decreases as a function of temperature. And then one finds that there is a characteristic temperature at which the resistance basically sharply drops to zero. And below this temperature, which is the superconducting transition temperature, the resistance essentially is equal to 0. This is shown here, that the resistance comes down, the metal comes down, and then the metal becomes superconducting at the Tc, the critical temperature, and the resistance is 0 below that. If this transition didn't take place, then the resistivity will be something that looks like this. It will continue to decrease, but it will go to a finite value at 0 degrees. So this is a very unusual phenomenon that below this temperature, the system can carry current without any dissipation, which is sort of similar to the superfluidity that we are talking about here. But it's a superfluidity now in an electron system, not in a system of helium-4 molecule atoms. So one has to understand what is going on and so on and so forth. So the zero resistance is one of the sort of most striking property. But there are also other properties of the superconducting state that makes it very special. And I think there will be some animation here, which illustrates one of these properties, which is known as Meissner Effect, which says that the superconducting state basically excludes a magnetic field from penetrating inside the superconducting state, which I'll come to in more detail. But the superconducting state has very strange magnetic properties. And one of these properties is that it doesn't want to be in a state where in a region in space where the magnetic field is large, because it has to exclude this magnetic field from its inside. So that leads to this thing called levitation effect, that if you have a magnet here, at the bottom you have a magnet, and you have a superconducting sample, and then you just release it slightly above the magnet, then it levitates, basically. It doesn't, there is a gap between the magnet and the superconductor, and superconductor sample basically sits there. And the reason it sits there, doesn't fall under gravity, is that because there is a strong magnetic field here, the superconductor doesn't want to be in that region. So there is apparently a force which is upwards, which balances the force due to gravity. And as a result, it sort of hovers at some height above the magnet. So this illustration, I'm sure many of you have seen in various labs when you have this outreach programs and things like that. This is one of the simplest experiments that one can show. So zero resistance and expulsion of magnetic flux. These are the important properties of this superconductor. So I will not be able to go into the real theory of superconductivity, because that, of course, involves quantum many-body problems and so on. But I will try to give you a sort of physical picture of why this system becomes superconducting at low enough temperatures. And that physical picture was, it's called the Bcs Theory of Superconductivity. Bardeen, Cooper, and Schrieffer. These are the three people who are involved. And again, they got the Nobel Prize and all that. It's a very famous theory which illustrates, again, another very important emergent phenomenon. That emergent phenomenon is the occurrence of the superconductivity. The superconducting state, as I just mentioned, has quite unusual properties. So roughly speaking, a superconductor is sort of like a superfluid. We have seen that helium-4 liquid undergoes a transition at low enough temperatures to a state where the fluid can flow without any viscosity. So the equivalent here is current flowing without any resistance. Because the charge here, we're looking at electrons. So they carry charge. So when they move, then there's a current associated with it. And superconducting state is one in which you can have this current, but there is no resistance, no dissipation, no friction that tends to reduce this current. The current can keep on flowing without dissipation. So it sort of looks like that, there is some similarity, that there has to be some kind of a condensate in a superconductor. But this condensate will be of electrons. But electrons are spin-half objects. They are fermions. Whereas to get a condensate, as you know from the elementary theory of post-condensation of an ideal Bose gas, this is possible only in bosonic systems. So although we have electrons in a metal, somehow they have to, in some sense, combine in such a way that effectively you get bosonic systems, bosonic particles, which can then condense. So one way of getting boson is basically combining two electrons. If you pair up two electrons, each of them have spin a half. So then if you combine, then you will get something which is an integer, 0 spin or 1 spin. So two spin half objects, if you combine, then you will get either get 0, which is a singlet state, or you can get 1 spin, which is a triplet state. And these composite objects then sort of can look like bosons, and they can condense. And then one expects a state where this Cooper pairs, these pairs of electrons, can flow without any resistance. And that would be the superconducting property that we are seeing in experiments. So the question is how these electrons can pair up. Electrons, of course, are charged objects, so they repel each other. They have the same charge, so they repel each other. So naively, one would say that there is no possibility that they would pair up to form a bound state. So there the new physics comes in, and this physics is associated with electrons and phonons. And I don't want to go into too many details of phonons and things like that. Phonons are associated with the ions that are sitting on a lattice. Of course, electrons are the conduction electrons that can move in the lattice. So this is a cartoon of a lattice where you have these positive ions which are sitting on lattice sides, and then electrons are moving also in the same space. Now, of course, electron negative charge is a positive charge. Lattice basically means that on the average, the ions are going to be at the lattice sites. Instantaneously, they will not, I mean, they have this degree of freedom of small oscillations or small movement about the lattice points. So when an electron comes in, or when an electron is present in this space, because negative charge, so this will attract the ions. This is what is shown here. Electron was there, so this basically attracts the ions. And so the ionic positions are a little different from what they would be in a perfect lattice. So this is called a distortion. These ional distortions are also can be described in terms of phonons, which is something that we'll not go into. But it's basically displacement of the ions from their equilibrium positions. And these displacements can be caused by an electron because the electron has a negative charge and it will attract the ions. Now, there is a very important physical fact that the electrons are, the mass of the electron is much, much smaller compared to the mass of the ions. So the dynamics of the ions is very sluggish compared to the time scale associated with the dynamics of the electrons. So once the ions have this distortion, it takes a relatively long time for the distortion to disappear. And during this period, when the distortion is still there, another electron can come into the same space, and then it will see a position which is in some sense lower energy, because the distortion was produced because an electron was there. So when a negative charge is there, the ions come closer, and that they come closer because that configuration will have a lower energy. Now the ions basically take a long time to relax from that changed positions, and so when another electron comes in here, it will see a lower energy. And so this is what basically leads to, in some sense, an effective attraction between electrons. And this attraction is very different from the standard, let's say, Coulomb kind of attraction or repulsion. It's a retarded potential because first an electron has to come and distort the lattice, then another electron has to come and then occupy the similar position, which will give you a lower energy. So this is a region of positive charge attracts a second electron. And so this is the attraction. It's not that one electron is attracting another electron. One electron is causing some disturbance in the ions, and that is more favorable for another electron to come there. And that as a result, there is some kind of an effective attraction between the electrons, although they have some same charge. So they have a Coulomb repulsion. Depending on circumstances, this attraction can, in some sense, dominate over the repulsion. And then one gets basically a effective attraction between electrons, which is the reason why these electrons can form bound pairs. And this was first pointed out by Cooper. So these pairs are called Cooper pairs. And these Cooper pairs, in a very sort of crude sense, behave like bosons, and then they can condense, and then you have a superfluidity. But the superfluidity is of superfluidity of Cooper pairs, charged objects, that gives you superconductivity. So this is basically a very back of the envelope or hand-waving explanation of why superconductivity occurs. But you can see that the transition that is going to happen there from the normal state to superconducting state is not going to be very different from what you have in the liquid helium, where you go from normal liquid to the superfluid helium, because again, the same kind of ordering is taking place, but the objects that are ordering, the condensate is now in this case formed of Cooper pairs, whereas the condensate in the case of superfluidity is composed of helium-4. So this is some understanding of why the system becomes a superconductor. There is also this Meissner effect, which I'll try to also explain as we go along. The Meissner effect is that if you have a metal which is normal, T bigger than Tc, then magnetic flux basically goes through it. But if it is becomes superconducting when T is less than Tc, then the magnetic flux basically skirts the superconducting sample, doesn't penetrate inside the sample. It actually does penetrate a little bit. So this is what I'm trying to say here. Magnetic field penetrates a small distance inside the superconductor, but this distance is a microscopic distance, and this is called penetration depth. It's order of hundreds of angstroms or thousands of angstroms, something like that, depending on the material. And this is the property that leads to this levitation effect, that superconductor doesn't want to have magnetic field inside it, so it doesn't want to come too close to a magnet, and that leads to this in this simple experiment that I showed you, upward force which balances the force of gravity, and the superconducting sample basically levitates, floats in space. So these are the basic phenomenology. There are many other things that one can study, and I will not have time to go into it. Just maybe there is one little bit of a film clip that shows this levitation in a better way. So you can see it very clearly that the superconductor is floating above this magnet. There's this, yeah. So they put some liquid nitrogen on it, so it basically is a superconductor now, and then it floats above the magnet. So, what is the origin of this Meisner effect, and what is the reason that you basically have this magnetic field which penetrates into a very small surface region of width equal to this penetration depth, which is microscopic length. So to do that again, as I said, the microscopic many-body theory of superconductor is quite complicated. But as I was telling you earlier, in the context of Landau theory, one can again construct a theory of the superconducting state, which is very simple, which is again, it carries the name of Landau, but also Ginsberg played an important role. So this is called the Ginsberg-Landau theory of superconductivity. And again, the idea is very similar to what we had earlier, that you have this order parameter field, superconducting order parameter field, which is a complex scalar. Why is it a complex scalar is something that would be difficult to explain, but you can think of it as a wave function of the condensate. And the wave function, of course, as you know, is basically a complex number. The wave function at a particular point is a complex number. And here the wave function is, the order parameter is the same at every point in space. So you basically have a complex order parameter, complex scalar order parameter, which can vary in space. Just like in the case of the Landau theory of phase transition, one said that there's an order parameter field which can vary in space. And one writes the free energy as a functional of that order parameter field. And being a complex scalar, only even powers are allowed, because the free energy, of course, is a scalar. So when it cannot depend on the phase. So you have this quadratic term, you have the fourth order term. And here is now something which is new. If we had a neutral superfluid, just like in the case of helium-4, then you just have the kind of terms that you had in the original Landau theory, where you would get a gradient psi squared. But now we have a superfluid which is charged, composed of charged Cooper pairs. So when that superfluid moves, it gives rise to a current, and current in turn produces a magnetic field. So the point is, this order parameter now has to be coupled to the electromagnetic field, because now we are talking about a charged object, and its gradient basically corresponds to the gradient of this psi gives you the superfluid velocity. And whenever that is non-zero, then there would be a current associated with that, and there will be a magnetic field associated with that. So one basically has to couple the gradient of this psi to the electromagnetic field, which is expressed in terms of this vector potential. So this is the usual term. Del cross A basically gives you the magnetic field. So magnetic field squared by H by 8 pi gives you the energy density associated with the electromagnetic field. And this coupling of the gradient of psi to the vector potential is also a standard coupling. It's a gauge invariant coupling, which says that if I make a change of gauge, in the case of electromagnetic field, one can add, let's say, a gradient of a scalar to this A, which doesn't change the magnetic field. So under that kind of a transformation, the phase of psi also has to change, and it changes in a particular way, which I have not written down there. But this is the standard way. You can couple the gradient of this psi to a vector potential, which remains, this whole thing remains invariant under a gauge transformation. So this, if you think of this psi as some kind of a matter field, then this matter field is coupling to a gauge field, which is this vector potential. And this coupling is through this kind of gauge invariant coupling of the momentum. Let's say if you look at the Hamiltonian of a charged particle in a magnetic field, then exactly you get these terms. You get the momentum operator here, and you get charge multiplied by the vector potential. And this is what makes the whole theory gauge invariant. So this is now the additional thing that, in addition to the usual Lambda theory, that we have to include in the free energy to describe the coupling of the superconducting order parameter field to the electromagnetic field. And this coupling is necessary because we are looking at a charged superfluid, and its flow basically causes electric field, which in turn leads to magnetism and things like that. So then again, given this, so I mean, this tells you about, depending on the physical situation that you're looking at, how the Landau theory that you want to describe, that you want to use to describe the ordered phase, how that changes. Here again, because you have complex scalar order parameter, you have this only even powers. But then, since a coupling of the electromagnetic field is present, then you have to consider also the vector potential and its coupling to the order parameter field. And then you do the same thing. You basically find minima of this free energy. Now there are two sets of variables. One set is this complex scalar field. Other is this vector field, which is a vector potential for the electromagnetic, for describing the electromagnetic field. And you have to minimize. I should have written here also A here, because it's not just a functional of this psi, it's also a functional of this A. And you have to minimize this F with respect to both psi and A. And when you do that, that of course requires some mathematics, but again, it's a fairly straightforward mathematics, which will tell you that when this average value of this psi is non-zero, when you are in the superconducting state, where the superconducting order parameter has picked up a non-zero value, then that leads to some kind of a mass turn for the electromagnetic field. This exponential decay of the magnetic field inside the superconductor. So if I mass term, then you have, see here, grad cross A mod squared. If you go to Fourier space, that gives me something like a k squared A squared. K is the wave number, and that doesn't have a mass term. But as soon as this psi is non-zero, then from here you pick up a squared term, which has this non-zero value of psi squared associated with it, and that term occurs in the same way as a mass term occurs in standard field theory. And the mass term basically tells you that the spatial dependence of this vector potential can be, depending on boundary conditions and things like that, an exponential function. And this is precisely what happens when you have a magnetic field and you put a superconductor in it. The magnetic field decays exponentially inside the superconductor, and the length scale associated with that exponential decay is basically the what it told you about the penetration depth, and that is what leads to Meissner effect. And these things request a little bit of calculation, which I don't want to go into, but the physical effect that I want to describe here in the context of superconductivity is that the Landau theory that you have for the superconducting order parameter, which is a order parameter is a complex scalar, for simple S-wave superconductivity. Different kinds of order parameter you will get for different kinds of superconductivity. This complex scalar is true for the simplest Bcs kind of superconductor, the S-wave superconductor. There has to be a coupling of that order parameter to the vector potential. And then one writes down Landau theory, which contains both of these fields, and then the usual minimization and things like that will tell you that the propagator for this vector potential acquires a mass, and the mass comes from this term, A squared, psi squared. And when psi average is zero, then of course this term doesn't contribute. When psi average is non-zero, then it gives you a constant times A squared, which looks like a mass term for for the vector potential, which in turn says that the propagator can fall off exponentially inside the superconductor, and the length scale associated with the exponential fall off is the penetration depth, which says that magnetic field, as you go from outside to inside, you have to put in the appropriate boundary conditions and things like that. As you go from outside to inside, it will decrease exponentially, and it will be excluded from the bulk of the system. And these are just words at this point. I mean, I don't want to go into this. The mechanism through which this electromagnetic field or vector potential is picking up a mass term, and has analogies with this Higgs mechanism that you may have heard about in the context of this high energy physics, elementary particle physics, where again gauge boson picks up a mass through its coupling to a matter field. So this is has analogies with field theory that you use in high energy physics to describe elementary particles and their masses and so on and so forth. And this was actually noted by Peter Higgs. In his Nobel lecture, he mentioned that this Phil Anderson actually pointed out that there is this strong similarity between what is happening, this Meisner effect, etc., that you have in a superconductor, and what you have in this these theories for high energy physics for elementary particles. So again, this is of course a very profound, in some sense, emergent process, in the sense that you start with metal and electrons, and you have the usual conductor, but then below a certain temperature, the whole behavior changes completely. And the two interesting things: one is zero resistance, the other is this expulsion of magnetic field. And one can understand many of these things from analogies with other systems undergoing phase transitions and other field theories, and so on and so forth. So, can you tell me how much more time I have?
We have just a few questions. Yeah, you can take up as much time as you want, so 5 to 10 more minutes.
Okay, so up to this point is basically what I had promised, that I have talked about magnetic systems, I have talked about liquid crystals today. I have also discussed some things about superconductivity. Of course, in 15 minutes, you cannot really go into the details. But the kind of ordering, the kind of order parameter, and its coupling to the gauge field, electromagnetic field, which leads to the Meissner effect, etc. Those things can be understood within a framework which is very similar to this Lambda theory, and one has this Ginsberg Lambda theory, which explains many things about the superconducting state, and there is similarity with some phenomena that one is familiar with in gauge theory. And of course, I mean, the superconductivity that I talked about is the sort of conventional kind of superconductivity, the Bcs kind of superconductivity. But now there are, more recently, there have been many other kinds of superconductivity that have been discovered from experiments. A theoretical description of this high temperature superconductors is still in some flux, in the sense that there are many theories, but nobody seems to agree with. I mean, there is no consensus as to which one is the correct theory. And still, many experiments are going on to understand what is the right description that gives you superconductivity at these high temperatures. So the remaining time, I want to give you a few more examples of such emergent phenomena. So my whole emphasis has been to sort of tell you about what an emergent phenomena actually is, and give you a class of examples. All these examples are taken from the theory of phase transitions. The phase transition and the spontaneous breaking of symmetry, these were the two themes of the various systems that I talked about. I talked about Ising model, Heisenberg model of magnetization, some models of particle systems where you go from liquid to a crystal. I talked about some liquid crystalline systems where different kinds of order can occur, transitional as well as orientational. And I've talked a little bit about superconductivity and superfluidity. The reason that I didn't go into the detailed microscopic description is that that involves some concepts, techniques of quantum many-body theory, which perhaps would not be very accessible to undergraduate students. So I tried to describe, even superconductivity, I tried to describe in terms of the simple Ginsberg-Landau theory, where you basically start with the free energy, write it as a functional the order parameter and then try to understand what that then predicts. But there are now many other examples of emergent phenomena. So I'll give you 3 or 4 examples of such an emergent phenomena. This is basically, again, looking at various electronic systems at low temperatures. And the electrons, of course, are strongly interacting with each other. And various new phenomena appear as a result of these interactions, which couldn't be foreseen simply by looking at the Hamiltonian of the system. And what is happening these days is that many of the things that people earlier had discussed in the context of, let's say, field theory and the theory of elementary particles. So you have heard about magnetic monopoles, right? I mean, the Dirac monopoles and things like that. Of course, I mean, in standard electromagnetism, there is no monopole, magnetic monopole. Del dot B is always equal to 0. But one can think of what would happen if there were monopoles. And there are some predictions also by Dirac many years ago of the presence of strings and when there are magnetic monopoles, etc., etc. Now the point is that people have come up with some condensed matter system where you have things which look very similar to magnetic monopoles. These are not the elementary magnetic monopoles that Dirac talked about, but these are excitations that look like the equations that govern excitations. They look very similar to the equations that you have when you describe magnetic monopoles. So I'll tell you a little bit about this system. These are, the name is pyrochlor, and a particular compound is dysprosium titanate. So I mean, this doesn't mean anything. The point is, I mean, these are crystalline solids, and they have units which are tetrahedra. So we have these 4 spheres that I'm showing here. They form a tetrahedra. There is a base, and then there is a top. There is a pyramid on top of it. And each of these vertices, there is a spin. There is a magnetic moment. And these moments are indicated by these arrows. And the interaction of these magnetic moments essentially comes from the electronic effects. I mean, the electrons have magnetic moments, spin magnetic moment, they can have orbital moment, and so on and so forth. So it's, again, a consequence of having electrons in the system. And those magnetic moments interact with each other in a particular way. They interact in a particular way in such a way that 2 of these moments have to point out and 2 of the moments have to point in to get a state of low energy. Okay. So, and that rule, 2 in, 2 out, is called ice rule, because this similar thing happens also in the structure of ice. But here we are talking about a different compound and a low temperature, and we're talking about a situation where you have this tetrahedra, and then you have these magnetic moments at the corners of the tetrahedra, and to minimize the energy, 2 of them have to point in and 2 of them have to point out. The analogy with monopole is like this, that if you have this configuration in a tetrahedron, then there is no monopole. One sort of thinks of it like, this, if you think of this as, let's say, flux lines, there are 2 flux lines going out, 2 flux lines coming in, and so there is no net flux going in or going out, and so there is no monopole here. But thermal excitations or impurity effects can cause one of the spins to be not there, or the spin can point in the opposite direction. So then you have basically 3 out and 1 in, or the spin is not there, then you have again an imbalance. And whenever you have imbalance, then in this analogy with magnetic flux tells you that there could be, I mean, you can associate that with the presence of a magnetic monopole sitting inside this tetrahedron. So thermal effects or impurity effects, which basically disturbs this 2 in, 2 out ice rule, then can be thought of as the presence of a magnetic monopole. This, of course, I mean, just words, but then one has to do the calculation to see how the magnetic field behaves in the neighborhood of such a tetrahedron in which there is this imbalance, and how a tetrahedron where you have this imbalance, another tetrahedron where you again have this imbalance, what kind of behavior, magnetic fields you get between these 2 monopoles. And this people have done, and they find that the behavior that you get when you have this imbalance, instead of 2 in, 2 out, you have imbalance between in and out, then the magnetic behavior, magnetic field that you get surrounding that, and the magnetic field that you get in between to such defects, though they look very similar to what you would have if you had really a magnetic monopole. So there are many such studies being done, and as you can see here, there is a study which says that emergent phenomena, as an emergent phenomena in condensed matter physics, one gets this electromagnetism. The equations that describe the low energy physics of this kind of systems actually look very similar to what you get in electromagnetism. So this is, again, there is no reason to expect that if you have a solid state system, you have electrons and ions, depending on the interactions that you have among these objects, one can get to a state, to a phase where the low energy physics is described by equations that look very similar to electromagnetism. So this is a problem of much recent interest, and the fact that in these systems the excitations can look like magnetic monopoles. I'm sure you have heard about this is this fractional quantum Hall effect, which led to Nobel Prize for 3 people. These two, Stormer and Swede, they are experimentalists, and Laughlin was the person who developed the theory. Again, quantum Hall effect, I'm sure you have seen in experiments in the lab. So you have a slab here, metallic slab, and then you have a current, and you have a magnetic field, which is normal to this phase. And the current basically, of course, develops some kind of a voltage difference between these 2 points. But in addition to that, if we have electrons or holes in this material, they get deflected by the Lorentz force, and so there is also a off-diagonal voltage these 2 points in the y direction that develops. So this is the current in the x direction, magnetic field in the z direction, and then this Hall voltage develops in the y direction. And one can measure the ohmic resistance, which corresponds to the potential difference divided by the current in the x direction, and similarly Hall resistance, which is the potential difference divided by this current now. So that's why it is called off diagonal in that direction. And what people found in very careful experiments on very pure samples of 2D samples. So there are electrons which are free to move only in 2 dimensions, and then you have a magnetic field which is perpendicular to that system of electrons, the plane in which the electrons are moving. And then people did experiments, and then they found very strange behavior. So I mean, you see this line, which is sort of like a diagonal, that looks like that is the plot of the Hall resistance, and the line that goes up and down, that corresponds to the diagonal, the ohmic resistance. And this behavior were explained by theory, which was formulated by Bob Laughlin. And there is one thing that I wanted to mention a little bit in detail is that many of these quantum many-body systems, one is of course interested in the ground state, what kind of a state it is, but one is even more interested in excitations from that ground state. And there are certain kind of excitations which sort of behave like independent particles, which are called quasi particles. So what Laughlin did was he constructed an appropriate ground state for this kind of a system, which is basically a system where you have 2D electrons in a magnetic field, which is perpendicular to the plane of the electrons. And then once you have the ground state, then you can look at excitations, look at these quasi particles. And he showed that these quasi particles look like as if they have charge E/3 for a particular state. Not all of this, I mean, but all of these states are characterized by fractional charge, but the one that I'm looking at is 1/3 filling of the Lambda level. This particular plateau that you have here and the corresponding 0 diagonal resistivity. To understand the state of the system here, Laughlin showed that this can be understood from a particular construction of the ground state, many-body ground state for this system. And excitations from that ground state carry charge E/3. And so this is basically what I said here. Fractional charge, fractional statistics also, which is something that I don't have time to get into. But this fractional charge, again, something that one wouldn't certainly predict, because all the electrons that I have in the system are still charge E. And you have electrons that are interacting with each other, and they have a magnetic field. So it's impossible to predict that you will have excitations that look like as if the charge is E/3. Whereas this was predicted and also verified in experiments. And that's what actually led to this Nobel Prize. just one or two other systems if you have want to listen to me for 5 more minutes, because these are interest. This is again another system, one-dimensional system of electrons, and then one is looking at basically the electronic properties of such a system. And of course, electrons, as you know, have a charge which is minus e, and also have a spin which is half. And these two always go together. That's what he thought. But in this one-dimensional systems, one can actually have situations in which the charge and spin degrees of freedom separate. The system where they now are called of an electron, which is again something that you may have heard before when you talk about semiconductors, for example. There are hole type carriers and neutron type carriers. So this is that you have this electrons here, and then one electron is missing. So there is a hole there. Spin, when this electron was there, they were up, down, like that, antiferromagnetic. But when this is missing, there is a down, but there is no up. So there is a net spin here. So the spin basically is there, but the holon can hop, and the holon has moved away here. So the charge degrees of freedom is associated with this point in space. The spin degrees of freedom associated with this point in space. So there is a separation of spin and charge. Again, experimentally people have found, and there is a theory that explains how it's going on. So I mean, otherwise, again, you know, if you had an electron in elementary particle physics, then you would say that the charge and the spin go together. But here in a condensed matter system, because of strong correlations of the electrons, these two degrees of freedom can separate, and you can have two quasi particles, one carrying charge, one carrying spin. This is a last transparency. I again will not have time to go into all of this. So there are various elementary particles. In field theory, people postulated many years ago. Majorana and Weil, they postulated kinds of elementary particles, fermions, that has some specific properties, which were not observed in experiments. I mean, one didn't find elementary particles with those properties, but now one is finding quasi particles in condensed matter physics, which have properties very similar to this Majorana and Weil fermions. There is a new subject which is very important, or very attractive, or very popular these days, which is called many-body localization. See, this whole thing that I have been discussing today sort of assumes statistical mechanics, system equilibrates. I mean, there are, of course, these special cases when you have this symmetry breaking and so on that we are discussing last time. But the whole framework was based on some equilibrium statistical mechanics. But now people are finding that there are some quantum systems that don't equilibrate. So you cannot use the standard statistical mechanics framework for describing those systems. And that also happens because of this effects coming from strong interactions and things like that. So just wanted to point out that there are now many body systems where people are finding phenomena that are quite unpredictable from the starting point, where you just have, let's say, electrons and ions. In a solid state, you always have electrons and ions. And because of strong correlations, strong electron-electron interactions, one is finding very exotic ground states. And the excitations from those exotic ground states have, again, very exotic properties. And these are very good examples of this phenomenon that I've been trying to illustrate, trying to call emergent phenomena. So there are also some other things, but there is no time. So this is the first part of the lectures. I mean, this was the basic objective, to sort of give you illustration of this sort of phenomena that were pointed out by Phil Anderson in his paper, which is more is different, collective phenomena, new physical effects arising from collective behavior in a large number of interacting objects. And I've tried to give you some examples of such phenomena. I also tried to give you some idea about the theoretical framework within the Ginsberg Landau theory or Landau theory, things like that, that one uses to describe this phenomena. But I mean, to get more deeply into it, of course, you have to have more involved theory, which I try to avoid because many of you will not be familiar with that. So I hope I've given you some overview, some picture of these interesting phenomena associated with strong interactions of a large number of particles. So there's one more lecture, of course, and tomorrow I'll discuss something which is a little different, physics of disorder. So I think this ends the part that basically deals with this emergent phenomenon. If you have questions, then happy to address.
Thank you, sir, for your insightful talk. Before moving on to the question and answer section, I now request all the people who have joined in to switch on their cameras so that we can take a Google Meet screenshot with our speaker. After it, we shall resume with the question and answer session.
Okay, so my camera is already on, so you can probably see me.
Yes, sir. So if you can stop presenting, we can get the time.
No, I never did that.
Hello, Chandan.
Hi.
We've got the screenshot. Thank you.
Okay.
Thank you.
So now we'll be moving on to the question and answer section.
Hi.
In order to make it more understandable, I'll also be posting the question in the chat box, sir.
Okay.
So if you can't, in case you can't hear me or cannot follow me, please look at the question in the chat box.
Now, today the audio is better, so I think I can understand. I should be able to understand. Anyway, yeah.
So the first question is, how can you restrict the electrons to 2D motion in experiments in quantum Hall effect experiment?
Okay, so this, of course, I mean, there are many different ways in which you can have a two-dimensional system of electrons. What you have to have is basically a potential that restricts motion in a direction which is perpendicular to the plane in which you want to put the electrons. So these days in semiconductors, one can do that. One can have different layers of semiconductors in such a way that it's favorable for the electrons to be the interface between two such layers. And then there is a confining force, which is normal to the layers. So in that z direction, you can solve the Schrodinger equation and you get basically a bound state. And if the energy levels associated with those bound states are sufficiently far away from each other, then you can say that at low temperatures, system will be only in the lowest of these bound states. So there is no motion. So there is motion, but I mean, there is a single quantum state in a direction perpendicular to the layers, but they can, of course, free to move around in the layers. So that is the standard way. Quantum Hall effects were done with this quantum, the superconductor, not superconductor, semiconductor heterostructures. But there are other ways of also getting layers of electrons. For example, if you have liquid helium, there's some experiments like that are going on actually in IASC. Liquid helium, on the surface of that, you can again localize a set of electrons, which will, because of interaction with the surface, they will not go out of the surface, but they will basically interact among each other on the surface. So yeah, it's not obvious how to get a two-dimensional system, but in the quantum Hall experiments, as I said, it's a semiconductor heterostructures. Oh, I should mention also a third situation. There are some layered structures, crystal structures. Crystal structures where you have again a layered structure, and the spacing between layers is relatively large. Whereas the spacing between two lattice sites, which are falling on the same layer, they're small. So the electrons in one layer and the electrons in its adjacent layer, they can attract only very weakly. And again, in that case, the basic physics will come from the interaction of the electrons which are in a particular layer. Whereas, as a perturbation, one has to sometimes also take into account the interaction between electrons in different layers. But as a first approximation, one can say that each layer is behaving independently. And that's again a two-dimensional system of electrons.
The next question is, it was pointed out that in superconductors, the attraction between electron pairs is different from the usual Coulombic one. Can you elaborate on that?
Roughly speaking, this should be clear from the mechanism that I tried to illustrate. That, you see, if I look at the standard Coulomb interaction, then you have two electrons, one at R1 and one is R2, and then there is a Hamiltonian in the term that is basically E squared divided by R1 minus R2. This is a kind of Coulomb repulsion and the corresponding term in the Hamiltonian. But here, when you are looking at electron, the interaction between electrons mediated by the phonons, there is time in the picture. In the sense that this picture that I tried to illustrate is that one electron, let's say at time t equals 0, was near a particular point. One electron was near a particular point in the lattice. It caused some lattice vibration, lattice distortion, described in terms of the phonons. And this distortion is such that it reduces the energy. I mean, another electron, it's easier or energetically more favorable for it to come and sit at that point where the distortion was produced. So there is a time difference between these two, that one electron goes through and subsequently another electron comes to the same point and finds the same environment, which gives you a lower energy, and that effectively one describes in terms of some kind of an attractive interaction. So there is a frequency dependence or time dependence of this interaction, attractive interaction that you get modulated, mediated by the phonons, by the lattice effects. So it's called a retarded interaction, which is quite different. I mean, at least in a non-relativistic description, one would say that the electron interaction is, there is no time in it. It's instantaneous. Whereas the interaction that you have between electrons mediated by the lattice has this essential time dependence or frequency dependence. That way, these two are quite different. And this frequency dependence is very important.
So with that question being answered, we have come to the end of today's lecture. Thank you, sir, for your very interesting talk. I also request all the people who have joined us today on Google Meet as well as YouTube to be with us tomorrow as well. Thank you everyone for joining in. With this, we end the meet today.
Okay, thank you very much.
Okay, thanks.
Thanks a lot. Thanks a lot.
Thank you all. Thank you, sir.
And I'll be there tomorrow also. So if you have some questions that you can think of, between now and tomorrow, then again we can address. I mean, it's not necessary that tomorrow's questions will be only dealing with tomorrow's lecture. So that also is possible.
Sure, sir.